Hello, I'm Associate Professor Benjamin Holcomb. I'm a member of the Centre for Audio Acoustics and Vibration at University of Technology, Sydney. I'm here in our acoustics labs at our botany campus, UTS Tech Lab, and this video is just to demonstrate something that we've been working on for several years now, which is a technique known as continuous scanning laser Doppler vibrometry. This is my scanning laser vibrometer, and I'm using an external signal generator to drive the X and Y mirrors within the scanning vibrometer such that the laser beam is scanned around in a nominally circular profile around this axisymmetric steel ring, which is an example structure for which we understand very nicely the expected vibration behavior. We're essentially modulating the sine and the cosine to produce a varying amplitude circular scan with different frequencies for the scanning and the modulation of the radius of the circle. I'm exciting the sample with Qsources LWS lightweight shaker, a mini-inertial shaker. In combination with our laser vibrometer and the lightweight shaker, we have very, very low mass loading and stiffness loading of this sample, which means that we can get measurements of its dynamics and characterize its dynamics with very high accuracy and produce some very nice experimental data in terms of natural frequencies, resonant frequencies, and mode shapes. I'll show you how we do that on the screen over here from the continuous scanning laser vibrometry standpoint. Here you can see a video image being captured of our continuous scanning measurement in very nice resolution. That's coming from a camera that's integrated within the scanning laser Doppler vibrometer. In terms of the time domain data, this is shown in this top plot here. And essentially what we've got here is the vibration frequency of the ring with the very fine lines within this time domain plot. I'm exciting this structure at close to its first resonant frequency, which is 342.6 hertz. And that's the spacing essentially of these vibration signals here. That vibration signal is enveloped essentially by this profile, which is a function of how we're scanning the laser beam around the ring. And as well as our 1 hertz circular scan, we have a 20 hertz modulation of the scan. And so this modulation includes information both about the 1 hertz, so that's the low frequency enveloping here, but you can see additional enveloping on the peaks of our vibration signal, and that's because of the radius modulation. Of course, for this ring in its first resonant frequency, it's an axial mode, so the motion is out of plane. There is a modal diameter, and we have data that we've captured subsequently to characterize the vibration of the ring in a traditional scanning vibrometer way, and I'm demonstrating that in an additional video. These time domain data, however, allow us to, in theory, with only 2 seconds of data, that might allow us 10 averages, let's say, or 5 seconds of data if we want to do a little bit more noise suppression, produce very quickly information about both the resonant frequency and the mode shape, or operational deflection shape, I should say, in this case, of our axisymmetric structure. And if I do a quick fast Fourier transform of these time domain data, you can see the way that we can do that. So our resonant frequency is at this central peak here, 342.6 hertz, as I mentioned. We have sidebands about that primary vibration frequency that are actually larger in amplitude in this case, and further sidebands at other distances away. The distance between the primary vibration peak and each of these pairs of sidebands is a function of the frequency of the circular scan and the frequency of the modulation. So from the main peak to these 2 sidebands, I have my circular scan frequency separation, and to the subsequent sidebands, I have a spacing that's a function of the rate at which I'm varying the radius of the scan. So in principle, this frequency spectrum contains all of the information, and I'm able to do post-processing on these data to produce as I've mentioned, the resonant frequency and mode shapes for this particular structure very quickly. And the things that we're working on currently, that we're essentially extending this capability beyond the current state of the art, includes smart ways to suppress the inevitable noise that we have as a result of things like laser speckle and other challenges. And we'll be producing research papers in the future and subsequent videos to explain how we're doing those kinds of things. Thank you for listening. I've been Ben Holcomb from UTS, and I'm here in the Tech Lab facility, our acoustics labs, talking about continuous scanning laser vibrometry.